So this work, this is a recent project, storage and retrieval. Just maybe to give a little bit of background, I like looking at problems that involve planning for movable bodies, a lot of movable bodies. So this will be one of them. And many times these end up being intractable, NP-hard, or worse. And this is one of the first ones that I looked at that surprised me. It was surprisingly easy. Hopefully not too easy. So let's go ahead into the motivation. So we have storage is a very big thing, as you know, and it's very common to store things. We have storage systems to use uniform size loads, right? Loads is what you store, and uniform size means they just have the same dimensions or can fit in the in designated spaces that are in the same dimensions. And these are increasingly incorporating automation solutions. So you don't want to do these things yourself when you retrieve or store something. You want some system to help you do that. So there's lots of examples here, from automated parking to container terminals with cranes that do a lot of this job for us. So what is our main question here? There's an inherent trade-off between what we call rearrangement and the storage density. So by rearrangement, I mean the relocation of loads within the storage area when you want to access something. So on the one hand, you can create setups using aisles where if you want to get to something like in a supermarket, you can just grab it directly, but you're going to waste space doing that, at least a third of the space actually. On the other hand, right, if you want to pack your storage area, completely fill it, and if you don't do things the right way, when you want to get something, you're going to end up digging through all the loads to find what you need. So this is the main question that we study here. How to maximize storage space utilization while minimizing the costly rearrangement efforts when you want to get something. Within this broader motivation, we study a specific setting which involves storage. So first, all the loads are stored in some order, and then they are retrieved in some other order. This may seem a little bit restricted, but it actually fits a lot of natural motivations. You can think of a distribution center where suppliers have to first stock a distribution center, and then some other trucks come and pick up loads to retailers. This happens in Amazon's supply chain, for example. So the point is you have some temporary storage area. Things are coming in and then they have to be retrieved. And you want to be as efficient as possible in terms of your space usage and the time taken to retrieve things. So let's look at our problem formulation. So we ground this to a 2D grid setting. And each load can occupy a distinct cell in the grid. The loads are labeled. And we assume that the axis happens from the bottom row of the grid. So I'll call it the bottom row, the first row. So the other sides of the grid are just walls. We can assume that before we store a load or retrieve a load, it can just appear or disappear on the bottom row, on whichever column we're interested in. And what we'll be measuring here for the most part, not only, but for the most part, we're focusing on actions. So what is an action? An action is moving a load via collision-free path, and there's three types of actions, right? So you see that here. You can store a load, you can retrieve a load, and you can also relocate it on the grid, and this is the bad action that we want to avoid. And yeah, just in case it's not clear, so the density here, when I refer to the density of the storage area, it's just the number of loads divided by the number of cells in the grid. Please let me know if you have any questions on the setup.
What is the cost of actions? Is it one per action or the amount of movement? Or...
Yes, so that's a very good question. So primarily we just count the actions. Where the motivation from that comes from the fact that loads are oftentimes very heavy. So you have to, if it's like a robot that moves the load, it has to come to it, slow down, stop, pick it up, load it, and then start moving again. So actually that can be a big bottleneck, just the act of picking and dropping off a load. Although distance does matter too, and I'll say something about distance too. That is not our kind of main perspective here. Let's just give an example of our concrete formulation here. So given this storage area and an arrival and departure sequence, forgive me for sometimes switching terms of it. I might call it a retrieval sequence, retrieval order. So given these arrival and departure sequences, we want to output the actions that first store all the loads, and then retrieve them per the given sequences. And our objective is minimizing the total number of actions. So let's look at this example. So yeah, well, without loss of generality, we can always relabel the loads to depart in the order 1 through n. So let's look at this arrival order here. We can store the 9, followed by 4, followed by 7, and slide it in just like that. And so on. I hope that the idea is clear. And you can notice already, hopefully, that after storing the loads this way, we can actually retrieve them without any relocations. So this is the best possible solution. With 2n actions, that's the minimum number of actions. Now, to make this a little bit more, to add some more flavor here, we also consider various information assumptions. So you might not know these storage and retrieval sequences in advance. Maybe you'll know maybe you'll only have some partial knowledge. So we'll see how that affects the problem. Okay, so what are our main results here? So let's look at the different settings here. So you might have, in the worst case, a fully online setting. And I should say, yeah, just the first question that we ask you is just, can you get to rearrangement-free solutions, such as the one I just showed? So suppose you don't know anything about the arrival sequence nor the departure sequence. In that case, you must limit your density to at most 2/3 to guarantee a solution without rearrangements. And now suppose you know the departure sequence, but you don't know the arrival sequence. So that means that when a load arrives, you do know its position within the departure sequence, but you don't know when the load is going to arrive. So already here, we can avoid rearrangements if we're able to keep one column empty with only one load in it. And conversely, we also show that if there's a full density, then you might actually need to do rearrangements. So this is almost tight, right? I mean, if you keep a column, you have to keep one column free, the grid dimensions tend to infinity, you almost fill it up, but there's a little gap here. But what is the result that was kind of surprising? If you know both the arrival and departure sequences, you can always avoid rearrangements. The only condition is actually very weak. You only need to have 3 or more columns in the grid. That means the open side of the grid is at least 3 columns wide, and that's all you need. And all of these are accompanied by, yeah, I guess I forgot to mention the aisle arrangement here. That's okay. These are all accompanied by pretty simple algorithms, linear time, or near linear time, depending on how you want to do it exactly, or your information requirements. So basically, we were able to eliminate the rearrangement density trade-off through some information. Okay, the order in which I'll go through these. So this is, I think, the most interesting result. So I'll just focus on this one. I will just mention these two a little bit faster. That's kind of the outline of the talk. We have some additional results here. So we provide a characterization here. If you have like a bound on the maximum number of actions that you're willing to have per load, then we provide a tight relationship to the maximum density that you can have. So it's 2/3 if you just want to directly access everything. It becomes 4/5 if you allow 2 actions per retrieval, and so on. And another result here in the partially offline cases, we can actually find an approximate solution if the opening of the grid is at least as wide as its height. Some related work here. So this type of ordered storage and retrieval problem has been actually studied quite prominently, or similar problems, for what I call stack-based settings. So these are motivated by the cranes in shipyards, and the access type there is different in the sense that you can only store, or actually you can only move a load if it's at the very top of a stack. So items are in stacks, and that changes the constraints quite significantly, and actually results in an NP-hard problem, even to determine if 0 relocations are possible. Similar question was asked for train yards. So you can think of this as maybe like a tree. but it still has this last in, first out structure. There's some other related problems that are also NP hard. So as long as we have stacks, these problems are NP hard. Some other related work concerns, there's this theme of puzzle-based storage, which is actually quite similar to our setup, where we can have loads on a 2D grid with robots that can move them, or maybe the loads can move along conveyors. But the questions asked here are actually different. Generally, they look at what if you want to retrieve one or a few loads. So it's kind of a pretty random setting. You don't know much in advance, or you don't necessarily have a storage phase. So that's that. Okay, let's look at the results. I was quite surprised. I mean, we were quite surprised when we first noticed this. It seems at first glance not intuitive that you would always be able to avoid relocations as long as you have an opening with 3 columns or more, right? Because if you think about it, if you only have a width 1, you're essentially in a stack, right? So it's last in, first out. With 2, you're almost at a stack. And already with 3, you're good. And this is, of course, independent of the height of this grid, so I can have it as long as I want here and still have no relocations. I'll just quickly show why, if you're with this 2, you might need to do relocations. So this is an example. So suppose my arrival, I have a load arriving at load number 1 arriving. It has to be placed on the front row because it's going to be the first one out. So let's assume it's placed on the left side here. Then the 4 has to be placed in the back, right? I can't just put it in the front and block access to the other empty cells. And then we have no choice, right? We essentially have a stack here. 2 comes in, and then 3 comes afterwards, and they have to be placed this way. And you can hopefully already see, well, I'm going to have a problem for 2, right? 1 can be retrieved, but 2 is going to be blocked. Okay, let's just, before I present the algorithm here, I just need some few preliminaries. But just to be clear, an arrangement, when I say an arrangement, I mean an assignment of the loads to grid cells, so it's a bijection. And we're interested in finding arrangements that allow us to work with a certain departure or arrival sequence. So we say that an arrangement satisfies the departure sequence if all the loads can be retrieved in the order specified by that sequence with 1 action per load, in other words, with no relocations. We can define the same notion for arrivals. So in this example, this arrangement satisfies 1, 3, 2, 4, and obviously other orders as well. Okay, so some simple observations. So if we satisfy a certain arrival sequence, right, that just means that we actually satisfy the departure sequence in which we reverse the arrival sequence, right? You can just reverse all the actions and all the paths remain the same, just the movement occurs in the opposite direction. So we refer of finding a rearrangement. Yeah, go ahead.
Yeah, I'm just why you always consider square 3 by 3, 2 by 2. So what is going to
We do not consider only squares. It was just, I guess the example so far only consists of squares. Yeah. So again, our goal is to find a rearrangement-free solution, and we can reformulate it based on our observations, or well, only one observation so far, really, as the following problem, right? We just want to find an arrangement, that is how to store the loads on the grid, so that 2 departure sequences are satisfied. So we switch our thinking now to just look at the departure side, and the sequences are obviously the original one, and now the arrival one in reverse. Yeah. So fairly simple, I guess, so far. Well, then how can we check if a certain departure sequence is satisfied? Well, there's an if and only if condition here, right? We only need to have each load be adjacent to a load that departs earlier, or just be on the bottom of the grid.
what's the motivation for this problem? This one. As in two orders.
So our goal is to, I want to now prove our main result for the offline case, which is that we can always find a rearrangement-free solutions if we have an opening of 3 or more. And this is just another way an equivalent way of phrasing the problem. Find an arrangement, so that is an assignment of the loads to the storage area such that these two departure sequences are satisfied. So that means we can retrieve them in the okay. Yeah, sorry if I missed something, please stop me if I did.
I like reverse.
So we need to satisfy the original one. They need to go out in the order that's given in the problem, but we also need to be able to bring them in according to an arrival sequence, right? But that's the same as taking them out in the reverse order of that arrival sequence. It's equivalent, right? You can always reverse all the actions. That's kind of the idea here.
Okay.
In any case, for now, you can just, if this bothers you, you can just think of it. Let's just look at this problem of satisfying these two departure orders. I want to take them out in this order and in another order. I mean, this makes sense maybe on its own right? If you have some uncertainty on the departure order. And so, right. So there's a fairly straightforward local condition, right, for determining whether an arrangement satisfies a departure sequence. So given this departure sequence, I can retrieve all the item without all the loads without relocations if each load is adjacent in the grid to a load that departs before it or is on the bottom row, right? And it's a simple proof by induction, right? So if 4, for example, here's as an example of these conditions, I'll be using these arrows to illustrate them. So 4 is next to the 10. If I know that the 4 can be retrieved, right, there's some path to do that. So the 10 can just follow the 4 out of the grid. So it's fairly simple observations here. And we're putting them based on these. We're now providing an algorithm. So the algorithm will now work for, this is the case of 3 columns. And we'll generalize it to more columns. So we're given the departure and arrival sequences, and we'll treat the arrival sequence as a reverse sequence here. And the algorithm is actually fairly simple. So we look at the first 2 loads that have not been assigned yet to the storage area, and call them X and Y. So here the first pair would be 1 and 12. If these are different, X is not equal to Y, I assign X to the left column and Y to the middle column. So if we keep going, all right, we have 2 and 7, the same thing happens. Okay, now we get to the 3. What happens here? Well, now 3, right? It's actually the same load that's currently the first on both sequences. In that case, we actually go to the right column. And that is really the thing that makes this, or this is kind of illustrates why we need at least 3 columns and not 2, right? Because 3, if you think about it, for us to be able to get the 3 out, well, it has to be both adjacent to the 2, both adjacent to the 7. But there's no way to do that with only two columns and meet the adjacency condition. So we have to put it on its own row, on its own column. We keep following this, so we kind of have pointers running here. So we have 4, and then 1 has already been assigned. So we skip to 10. It looks like this, and so on. Okay. And we can already verify. So this is the first stage of the algorithm. There's 2 stages. And we proceed this way until some column becomes fully assigned. And right, there's 2 cases. Either we fully assign the right column, or we fully assign together the 2 left columns. So you can verify the local adjacency here, I think, fairly. It's not a very complicated argument, right? We have 2 departure sequences to verify this for. So for the natural one, the 1 through n departure order, well, obviously on the left column, we fill them according to that order, right? The only subtlety here is, wait, what about the right column? But because we iterated over both of these sequences in order, we know that each load in the middle is going to have a load that departs before it on the left side. Right? Maybe you have to think about it for a moment, but it's because we iterated over them in order simultaneously. So that's that. But what's the argument for the other one? Well, it's actually symmetric, right? We fill this column exactly according to the from bottom up to match our arrival list reversed. And for the same reasoning as just explained for D, we have these horizontal adjacencies. Okay, so hopefully we that was sufficiently clear. Yeah.
It's easy if you put the same right, no? So in the middle, you change the last 2 columns, no?
It's easier if I put the 10 on the right.
No, no, then you make the middle column to the right.
You want to fill it like that?
No, that's the last two columns just change. Does not work. The column with 8 to 7, 12 will change with column 3. And then what happens to the other right doesn't work.
So these two need to be adjacent. These two, I need to work with two columns here that are adjacent.
Good point. We need it because, yeah, right, yeah. You need them to be adjacent.
Yeah, I guess it is maybe a slightly subtle trick. That might require a little bit more explanation, but the point is that by doing it this way, and keeping these two
right.
adjacent, right?
Yeah.
Basically, it's kind of, you can think of it as a greedy approach.
You make them,
As soon as I assign a load to the grid, I already know that it has the required local adjacencies for both sequences. So yeah, it's a greedy approach here. But yeah, I didn't finish, right? I didn't finish. There's still two cases. I think I'll maybe speed things up a little bit. So we verify this kind of first, and this is really the main argument here. But we do need to maybe continue and see what. Okay, so what happens if we get to this situation? Okay, so we filled these two up, but we still have, right? We're still not done. So what you do now is you assign for the remaining loads. You look at D, you examine D, the departure sequence, and just assign them to the rightmost column in order, whatever is left. So I have 6, 9, and 11 left. So, sorry, 6, 9, and 11 are just going to be assigned in this order. In case there's confusion here, this is not how they're going to be stored. This is just how to find an arrangement that will tell us how to store them. And how are the adjacency conditions work here? Well, again, for the departure one, bottom up is fairly obvious, but we already know that because we iterated over the two sequences in order, well, we know that 8, 10, and 7 must have appeared before 6, 9, and 11 on the other list as well, and therefore we are guaranteed to have these horizontal adjacencies. It's pretty much this one argument that now repeats, so I think I will maybe go a little bit faster. The other case, right, so we're left with something like this, right? We need to fill this up, and here we just alternate. Perhaps I didn't say, right, I mean, if for the x equals y case, then these exactly appear in order for both sequences. So the adjacencies just go like that. And yeah, so what happens if we have these two columns left? Well, then we can assign the loads. We first look at A reversed and assign the remaining loads to the middle. This works because if we look down, we satisfy the adjacencies for A reversed, and if we look to the right, we know that we have 7 and 6 before 10 and 12. And similarly, we just switch. For the left column, we alternate and go back to the departure order D. So it's a little bit of playing around with it, but it's the same argument. And yeah, it wasn't intuitive at all that this would happen. It didn't seem like that this would be possible, but it's possible regardless of your sequences. Okay, generalizing to multiple columns is not very hard. How do we do this? We treat the C for -3 columns in the following way. So let's examine the R incoming loads. So R is the number of rows, so it would be we process them in batches of R. So here we would start looking at 10, 4, and 4, 10, and 6, and just to make it clear, this is now the arrival sequence, not reversed. I'm not thinking about this as a reverse sequence. It's actually the arrival sequence of 10, 4, and 6. And I can place them in sorted order. 10, 4, and 6 sorted according to departure. Why? Because I have the adjacent column to the right, which allows access to any cell on the column that I'm currently filling. So I keep this column filling approach until I'm left with 3 columns, and then I can just apply the algorithm for the 3-column case. There's a slight maybe slight thing to dwell on here, and it's the fact that throughout this algorithm, you don't actually need to know the whole sequence in advance. right, you're actually looking at R loads at a time. So you can kind of process them in batches. I guess I know this is maybe not the right seminar to mention this at, but you know, we were kind of also thinking about the practical considerations if this was actually used, and so this kind of seems like a nice fact here as well. Of course, here you do need to know everything else, but that again just requires knowing like something like not something, but 3R. The next 3R incoming load suffices to basically get the whole algorithm to work. Okay. Oops. And a small observation, right? Because distance seems like a very natural thing to look at here. So these relocation-free solutions are actually distance optimal within they're optimal up to a constant factor. So, right, each path, we follow our local adjacencies, right? These specify the paths that the loads will take. So it means that each load will take a path that is within a column and maybe an additional side step, right, of one cell. Horizontally, therefore, we just have an additive factor of 1 for each path. So in total, if you sum everything, we'll actually get an approximation for distance. Okay, let's switch to the what we call the partially online case. So now we have an online problem. We know the departure sequence. We don't know. Yeah.
Just a curiosity. What happens if you really from setting and I can understand, but if you put height as well?
So that's a very natural question. It's a good question. And here, there's actually a slight problem because it depends on how you think of it. If you're here on Earth, right, you have gravity, right? I mean, you can't really move a load until you move the loads above it, and then you're in the stacked case. So I think there might be some hardness there, or you might have to look at it carefully to see what's going on. It brings us back to the settings I mentioned earlier. However, we thought about this a little bit, and we thought maybe one motivation can be if you're in space. If you're in space, right, then we need to confirm this, but it seems that you can extend it to a 3-dimensional storage area, and you're no longer constrained, right? You can always access a load, even if the whole kind of grid column is filled. You can or not filled, but if it's surrounded by other loads in the grid column, you can retrieve it because they're not going to like, right, collapse or something. The loads that are would be above it if you thought about it here on Earth. So for space rearrangement, you know, this could work. Probably. Yeah, this needs to be verified. Okay. All right, so I'll just briefly go. This is a fairly simple result, or right. So suppose we don't want to use the last column, then we actually don't need to know the arrival sequence at all, right? It suffices to just know the departure sequence and the position of each incoming load in the departure sequence. And it's very similar to what you just saw. I'm just going to do it a little bit differently here. So I will basically assign each load a column. Okay, so the first, it's kind of a proof by example, but right, so in this case, you take the first 3 loads, you assign them to the first column, the next 3 loads, to the second column, you can extend this and so on, right? So there's no problem you can always use a straight upward path to store a load, right? So we can just do this as in the example here, 1 and 2. And for retrieval, well, you can always use sideway motions, right? So 1 to 3 are going to be out first. If there's somehow blockages within the column, we'll just take a step of 1 to the right and go down. And this will apply after you column by column, the same argument. And okay, so what if we still want to fill the whole grid up, right? I mean, kind of the whole idea is to get your bang for the buck. You want to use up your whole storage area, so we can still show that there's an approximation on the total number of actions of 1.125 or 9/8 if your number of rows is smaller than the number of columns. So if the grid looks like this with a wider opening, you can repeat the approach that I just showed you. I'm just going over it briefly, except you just have to, instead of a column filling approach, it now becomes a path filling approach. You define these paths. So the first path is just the corner here, and then then you have R-1 paths that are L-shaped path like this, and then you can continue defining paths with just columns as before. I'm going over this a little bit fast, but you can essentially fill them without relocations, and upon retrieval, the only relocations you might have are for the loads in the corner, right? Because when it comes, basically these paths are going to be retrieved one by one. So let's say once these purple loads are out, well, the only one that may be blocked from the green ones is the cross. And that would necessitate an additional action. Yeah, so turns out we can handle this case. You might ask, I think it's kind of interesting to see, well, what is the best we can do, right? Because it's not, is this the best? I'm currently not sure. I haven't proven that, but I can give you a quick lower bound that if we do want to use maximum density, then on any grid size, you'll always have to do, any algorithm might end up doing at least one rearrangement. And there's a fairly simple argument here. So, right, I need to show that any algorithm can be fooled somehow, right? So I will present an adversarial sequence. So we'll start with n. N is the last load to the part. And I will issue n, n-1, and so on in decreasing order. And at some point, if we examine the empty cells above the front row, they must form a path, right? If you think about it, well, let's just wait until, right, the algorithm slowly fills up the grid. At some point, we examine the second row, right? This argument only applies if you have at least two rows, otherwise it's a kind of trivial problem. So at some point on the second row, you're only going to have one load left, right? Sorry, one empty cell left. This cell will lead to a component, right? It must be one connected component for all the other empty cells. And this component is going to be shrinking until it becomes a path, right? I mean, this path, there might be a degenerate case where this path is just this one cell. But you will eventually have a situation like this. What do you do in that case? You flip this, right? You flip the table or flip the script. What's the expression? And you say, okay, now I'm going to arrive the remaining loads, but I'm going to flip the order. I'm going to start at one until one in increasing order for the loads that you have left, right? And at that point, the algorithm really has no choice. Right? What does it do? Let's look at this again as an example, right? So think about it right now. I have 1 through some x. I might have some empty spots here on the first row, but they don't really matter too much. Right? I will have to put something here, and the remaining, and I will have to put the next load I will put will have to be a load that departs later. And notice that all the blue ones that have already been placed in the first phase also depart after 3. So 3 at this point already I can say is going to have to be retrieval rearrangements. So we have this lower bound. So it's kind of nice to know that we can't really do much better than what we show. Okay, I will briefly finish with our remaining case here. Fully online case, we have no prior knowledge. So here we actually use the previous result. It's kind of nice to give us a complete picture. But the idea is that if I want to guarantee worst case, and this is a worst case bound, so you can maybe refine this analysis. But if your worst case bound is A actions each time you store or retrieve a load, then you have to limit your density to 2A over 2A plus 1. And we show that, so this was kind of phrased, we had to rephrase an existing result to obtain this. And we also show that in our setting, you can almost achieve this bound. And you basically use a natural aisle-based approach, right? So this is like your supermarkets, where you're going to waste at least a third of the space for aisles. And if you want to do a little bit more rearrangement, you can just double up, right? Or increase the number of columns used for storage while keeping some aisles. So you can generalize this, and this is what kind of the plot would look like for your optimal density given the bound on the number of actions. So it takes to get to 1, right? You actually, it seems like in the worst case, you actually do have to go through a non-trivial amount of rearrangements to do, or get close to 1, right?
Wait, I'm lost here. So it doesn't depend from number of columns, or
Yeah, so so these bounds, I mean, to get the optimal kind of 2a over 2a plus 1, you want the grid to be a multiple of 2a plus 1, the number of columns. Yeah, if it's not an exact multiple, I think you will lose a little bit, right? If you do the calculation, but it's just our result here is just kind of just paint the picture of what you could theoretically do without pinning it down to precise. Yeah, but I mean, it's sufficiently general, right? It doesn't
I mean, like, so again, so action, what is action? Action is you just move side.
You take a load and you take it out or you relocate it.
I'm ready. So you give it like if you have more columns, then you have more freedom, right? I'm not right.
So yeah, so this actually doesn't give you that. No, you don't have that here. It doesn't help you.
Okay.
So I think I get what you're saying, right? It's intuitive that if you have a shallow kind of grid, you should be able to do better, maybe.
No, I mean like if you fit like 3 by hand, then you don't have much freedom. The tree should don't.
No, I mean I see where you're coming from. I think the reason why the result is this way is because we're talking about a worst case bound. So if you want to meet this worst case one, you never know what's going to be the first one to be retrieved, right? And so you're going to have to kind of be very careful about how you place the loads, the arrangement of the loads, to get that A actions. I would imagine though, I think if you maybe do some experiments for random sequences, I think you will probably find that, and right, you might be lucky, right? You might eventually have more loads that are exposed, and I mean this is it's a curious question. If you do a slightly better analysis, like expected number of relocations or something like that, then probably would be better for a wider grid. Yeah. So that's our main results. I mean, these are all our main results. I'll just briefly mention some ongoing work because it was just kind of nice. I mean, I don't know. I didn't expect this problem to just be relatively straightforward and have this elegant solution. So we just a natural question that we asked, and we actually have something open here. Well, great. If this works so well for the fully online case, like when does it stop being so easy? What if you have some uncertainty, right? Because you might not know the departure sequence really with 100% certainty. So we introduced this notion, that allows the perturbed a departure sequence. So you allow loads that are at most k positions away originally to swap, depart out of order, right? So for k equals 2, if that's our departure sequence, we can allow some swaps. So maybe right, so 3 and 1 can swap here, we swap 5 and 4. And we want to be able to find an arrangement that is able to support these other additional departure orders. And we got some results for it that are not super tight yet. So in this case, you actually need 2k plus 3 columns to guarantee no relocations. And we're able to show that 3k plus 3 columns suffice. So previously, right, just kind of to recap, with 3 columns, it was enough, was sufficient. Now you basically kind of naturally, we quantify how much wider should your opening be if you want to support a higher degree of uncertainty. And it's linear, basically, in this uncertainty parameter k that we defined. It would be nice to close this. I was feeling like pretty optimistic based on the first result that I thought we would be able to get a clear algorithmic result that would match this 2k plus 3 bound. I don't have it yet. Then problems start becoming tricky. But we do have this upper bound that's not too far. Yeah, we implemented this just to do some experiments to see what it would look like. Right, this is kind of, you can think of the Amazon pods with a robot that can move them. So it was nice to exploit this, the structure of this problem to get these desirable solutions. And I think, again, this is kind of maybe practitioner mindset, but I wouldn't be, someone might be tempted, look at this problem and say, oh, this seems like a hard combinatorial problem. We're going to have these search procedures, use some heuristics, but no, this can be solved exactly, and even you can obtain best possible solutions. So I think this is kind of nice, and hopefully this can be extended, right? Some natural questions as well. Probably the biggest restriction that I see is what if we interleave arrivals and departures, right? Like you don't want to just do arrival and then retrieval. We're also considering parallel motion. I'm right now in a kind of robotics lab, so we want to introduce mini robots to see how we can speed things up. Perhaps, an interesting question for this audience is what if you have some irregular grids, maybe grids that have some obstacles, right? Because you can't necessarily have all the space be used only for storage. Yeah, so thank you very much. It was nice to give this talk. Yeah, feel free to ask anything.